Hi friends. So today we start lecture 52 on our helicopter dynamics course, and today I'm going to discuss blade motion in forward flight. So we are going to focus on the blade flap, lag and torsion motion. I'm Dr. Anjan Ganguly. Now in forward flight, as we have discussed before, the loading is periodic and therefore we assume the solution to be periodic. So beta psi can be represented as a Fourier series. So here you have a steady component, you have the 1c and 1s components, and then you will also have a 2c component, 2s component, and so on. So there will be terms like beta 2c cos 2 psi and beta 2s sin 2 psi and so on. So the steady component beta 0 causes a coning of the rotor tip path plane, and this is generally known as the coning angle. Now, you will hear a lot about this particular geometric plane known as the tip path plane, and this is the locus of the point swept by the blade tip. So this will become clear in the following diagram. So if we have a reference plane here and the rotor is spinning around here, then the locus of all these points which have the blade tips is known as the tip path plane, and therefore this particular angle beta 0 tells us what is the level of coning of the rotor. So essentially the rotor acts like a cone or looks like a cone, and therefore beta 0 represents where this cone is in space. Now let us look at each of the other components. So if we look at beta 1c, it represents the forward tilt of the tip path plane, and beta 1s represents the lateral tilt of the TPP. So let's look at each of these pictorially. So if we take the rotor view, the velocity is coming from front at size 180 degree. This is size 0 degree. Okay, so essentially we are viewing the rotor from the left. So if we look at the beta psi expression here, if we see psi 0 degree, that corresponds to sine psi is 0 and cos psi is 1, and psi is 180 degree corresponds to sine psi is 0 and cos psi is minus 1. So in both these cases sine psi is 0, so beta 1s term is dormant, and so the beta 1c term will be there, and so here it's going to be a positive term, it's going to go up, and here it's going to be negative because of cos psi is minus 1 and it's going to go down. So essentially then beta 1c is going to look like the tip path plane tilt in the longitudinal direction, and so this is a forward tilt. Now similarly, if we look at beta 1s, and now we have to take the view from the back. So essentially we have size 90 here, we have size 270 here, and so sine size 1, sine size minus 1. And therefore what we get here is the cos term is now dormant because cos psi is 0 at 90 and at 270, and the sine psi term becomes sentient. So we can see that this beta 1s is going to go up because sine psi is 1, it's going down, sine psi is minus 1, and so the net result is that the tip path plane has a lateral tilt, and this tilt is physically the beta 1s. Now if you think about the higher harmonic content beta 2c, beta 2s, they produce a distortion of the tip path plane, so you can visualize them as the wobbling motion of the tip path plane. Lag motion in forward flight, we again can expand the lag motion in a Fourier series because we know zeta is a periodic function of psi. And so you have zeta 0, zeta 1c, zeta 1s, and you have the higher harmonic terms which represent the wobbling effect. So if we look at zeta 0, if we think there are 4 blades, then each of these blades is going to have a mean lag angle. So essentially they are all lagging behind. Okay, that's what the word lag means. And therefore all the blades will have a motion like this. That's the picturization of the zeta 0 term. Now let's look at the zeta 1c term. So for the zeta 1c term, cos has to become active. So that's active at size 0 and size 180. So in these situations, we see at size 0 you have zeta 1c here, that's the lag, and here psi 1c essentially takes a forward component. So this is sometimes known as lead lag motion. Okay, lead means it's going in front, and again there are 4 blades, and of course the components which are here, they have cosine 0, and so zeta 1c is dormant there. Now let us look at zeta 1s. So for zeta 1s, we have to focus on the second side of the equation, and so again here psi mu is coming from forward, the velocity is coming here. Here you know psi is 90 degree, psi is 270 degree. These correspond to sine being 1 and -1, and so zeta 1s is active here, lag and lead lag. So these give us the physical picture of some of these terms, zeta 0, zeta 1c, and zeta 1s. Now let's turn to pitch. So pitch motion is typically represented as follows. And so theta is theta 0 plus theta 1c cosine psi plus theta 1s sine psi. And theta 0, of course, is the mean blade pitch. This is also known as the collective pitch. And theta 1c and theta 1s represent the once per revolution variation on the pitch angle. Now, actually, you can think of blade pitch as having two components. One is a component coming due to flexibility of the blade and the control system, and this is a dynamic component. And one is the commanded pitch from the control system by which the pilot controls the helicopter rotor. So that is something interesting. Essentially, this theta is being given by the pilot, and by giving this theta, which also includes theta 0, theta 1c, and theta 1s, the pilot is able to control the main rotor completely. Now again, just recall this particular diagram, which is very important. We already know that as far as the airfoil section is concerned, the velocity which it sees is u, and also we know that phi is up by ut. Therefore we can write this particular equation in terms of alpha is theta minus up by ut. This is a very important equation which will let you picturize the different loads which act on the rotor and so on. So pitch is different from flap and lag because flap and lag are essentially responses of the blade, but pitch is something which the pilot is actually putting in. So you can think of the pitch as the input which the pilot puts in, and then what he gets out of the rotor are the flap and lag, as well as some of the torsion response of the blade. Now lift changes due to blade pitch changes are large because alpha is directly related to pitch. And actually, a lot of the prediction problems of helicopter dynamics come in from this equation. You can see that the main problem is in the prediction of UP, which depends on lambda. And therefore, if you are not able to predict the inflow velocity well, you cannot predict the angle alpha well, and therefore you cannot predict the lift, drag, pitching moment and all at the blade section well. So this is a issue which really complicates the prediction of load problem as far as helicopter dynamics is concerned. So for a rigid blade, we can say theta is some theta control from pilot plus some torsional response you get because of the inherent flexibility which is there in the system, which here is being captured by a spring at the root. And for the elastic blade, theta would be theta control from the pilot plus some torsion here. And here torsion is there because the blade itself is flexible in terms of having a GJ or torsional stiffness. So again, to recapitulate, theta 0 is called the collective pitch, theta 1c and theta 1s are called the cyclic pitch. Okay, and collective pitch controls the mean blade force and hence the rotor thrust magnitude. So essentially, the pilot is able to control the rotor thrust through the collective pitch theta 0. Now, cyclic pitch controls the rotor tip path plane tilt and therefore the direction of the thrust vector. And we know in a helicopter, by controlling the thrust vector, the pilot can essentially control the direction in which this vehicle moves. Now, theta 1c controls the lateral direction of the rotor and therefore it's called the lateral cyclic. Theta 1s controls the longitudinal direction of the rotor and therefore is called the longitudinal cyclic. So these are so important that it's worth remembering these permanently. Theta 1c is lateral cyclic, theta 1s is longitudinal cyclic. Now, how are these communicated from the pilot to the blade is actually a quite complex mechanism known as the Swashplate. So here I have tried to draw a schematic of a Swashplate. So essentially the rotor shaft is here, there is a non-rotating ring, there is a rotating ring, there are some bearings here. So the pilot controls come here and then this rotating ring essentially moves around and through the pitch link it communicates this motion, so the swash plate motion, to the particular blade concerned. So remember the swash plate is tiltable, so through the tilt it gives the pilot theta 0, theta 1c and theta 1s. So the swash plate has two circular discs with bearings in between. The bottom ring is fixed, the top ring rotates. The pilot controls move the non-rotating ring of the swash plate and this motion is passed to the blades via the pitch links. Basically, the swash plate gives control inputs by the pilot to the blade. So it's a very important piece of the helicopter. And if you check out any helicopters, if you go to air shows or you are near any helicopters, you can observe the swash plate is a marvel as far as mechanical engineering is concerned. It's a very complicated device. So one of the aims of modern helicopter technology is to get rid of the swash plate because it's so complex, and therefore there is research on things such as swash plate less rotors and so on. So maybe using trailing edge flaps or some device like that in conjunction with smart structures to get rid of the swash plate. But as of now, you do have the swash plate as far as conventional helicopters are concerned, and these conventional helicopters rely on theta 0, theta 1c and theta 1s to fly. Also, just to point out, many of the drones do not use such a complicated swash plate. They use 4 rotors, for example, and then they may be able to use these 4 rotors to control the thrust directions by differential rotation speed. So that again is a different control mechanism. Maybe if we get time, we will discuss it later in the course. So I will end this lecture here and I will see you in my next video.